Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll discuss the limitations of Euler's formula and introduce Rankine's formula, and later we'll work out a numerical example. Now we have seen that Euler's formula can be applied only for a long column. So it is applicable only for long columns, and if you try to apply this Euler's formula for a column which is short or whose slenderness ratio is less than the critical slenderness ratio for the material of the column, then the formula gives excessive high load than at which actually the column fails. So Euler's formula cannot be applied for short columns. Hence, for short columns, we have to use the crushing load given by Pc is equal to sigma Ca, where sigma c is the stress at which the column crushes, or usually it is taken as yield stress of the material. Now, to check the validity of Euler's formula, we need to find out the slenderness ratio of the given column and compare it with the limiting slenderness ratio of the given material. So if the slenderness ratio of the given column, if it's greater than or equal to the critical value of slenderness ratio for that material, only you can apply Euler's formula. If it is less than the critical value of slenderness ratio, Euler's formula is not valid. So this is a main limitation. When it's a short column, you cannot apply Euler's formula, and it gives a large load than the column can actually support. The load at which the column fails due to crushing is given by Pc is equal to sigma Ca, and this is applicable only for short columns, whereas long columns will fail much less load compared to this load given by sigma Ca. So for long columns, we have to use Euler's crippling load or buckling load P is equal to pi square EI by L square. But for short columns, we cannot use this Euler's crippling load, because if you use this, it will give a higher load than actually the column fails due to crushing. So to overcome this limitation, Rankine's proposed an empirical formula which can be used for short as well as long columns, and he proposed like this: 1 by PR is equal to 1 by PE plus 1 by PC. Now in this case, PR is Rankine's load and P is Euler's crippling load or buckling load, and PC is crushing load for a short column. When it is a short column, Euler's load will give an excessively large value, and this term becomes insignificant or comparatively small with this last term. So when this is small, you can take approximately 1 by PR is equal to 1 by PC, or PR is equal to PC. So the Rankine's load will be approximately equal to the load given by PC. When it is a long column, PC will be large in comparison with the PE, and PC, when it is large, 1 by PC will be small in comparison with this term, or this can be neglected, and you can take 1 by PR is equal to approximately equal to 1 by PE, or PR is equal to PE. So in that case, PR will be approximately equal to PE. So this gives a reliable solution for any type of column, and this is proposed by Rankine, and it's known as Rankine's formula. And this formula we can reduce further. You can write it as PC plus PE divided by PE-PC. 1 by PR is equal to PC plus PE by PC-PE. PC plus PE by PE-PC. Or PR is equal to, taking the reciprocal, PR is equal to PE-PC divided by PE plus PC. or if you divide by PE in the numerator and denominator, you get PC. Dividing by PE here, you get 1, and PC by PE. So PR is equal to PC by 1 plus PC by PE. Now PC is sigma CA. You can substitute for PC and PE. PC is sigma CA. So sigma CA, and PE is pi square EI by L square. So sigma CA divided by 1 plus sigma CA. I'll replace by AK square, where A is the area of cross section and K is the least radius of gyration. So A cancels, you get sigma C divided by pi square E. L square, if you take here in the numerator here, you get L square by K square or L by K square. So sigma C by pi square E into L by K square. So you get sigma CA divided by 1 plus sigma C by pi square E into L by K square. Or you can write it as sigma CA divided by 1 plus alpha into L by K square. Now sigma C by pi square E is a material property. Sigma C and E are material properties. So it is a constant for a given material. So that constant is known as Rankine's constant. So sigma C by pi square is written as alpha, which is known as Rankine's constant. And L by K is a slenderness ratio of the given column. So you get Rankine's load as sigma CA divided by 1 plus alpha into L by K square. So this Rankine's formula can be applied to any column, whether it's short or long. It gives a reliable solution for any type of column. And let us work out a numerical example. A solid circular column 60 mm diameter and 4 meter long is fixed at one end and free at the other end. Find the safe load using Rankine's formula. Given alpha is equal to 1 by 1600 and sigma C is equal to 420 megapascal and factor of safety 3. So data given is length is 4 meter or 4000 mm. Diameter of the column is 60 mm. It is a circular cross section. So 60 mm solid circular cross section, and its diameter is 60 mm. Alpha is given, that is Rankine's constant is directly given as 1 by 1600. And sigma C, stress at which the column fails due to crushing, is 420 megapascal. And one end of the column is fixed and other end is free, that is the end condition given for the column, and factor of safety is also given as 3, and we have to find out the safe load using Rankine's formula. Now let us work out. Effective length of the column is 2L because one end is fixed and other end is free. So that is the end condition. One end is fixed, other end is free. In that case, effective length is 2L and length is 4 meter or 4000 mm, and effective length will be twice of that length or 8000 mm. Area of cross section is pi by 4 d square. Diameter is given as 60 mm. So pi by 4 d square, that is the area of cross section. Pi by 4 into 60 square, you get 2827.43 mm square. Now to find out the slenderness ratio, first let us find out the radius of gyration. Radius of gyration is root of I by A, where I is the least moment of inertia, but this is circular cross section. You have only one value for moment of inertia, which is pi by 64 d to the power of 4. And area of cross section is pi by 4 d square. So you can reduce this. Pi cancels 4 in 64 16 times, and d square cancels. You get d square by 16 inside the root, and when you take the root, you get d by 4. Or d by 4, diameter is 60, 60 by 4, you will get 15 mm as the radius of gyration. Now you can calculate the slenderness ratio as L by K. We'll substitute it here. Now the Rankine's buckling load is PR is equal to sigma CA divided by 1 plus alpha into L by K square. Sigma C is given 420 megapascal. Area of cross section we have calculated, you can substitute it. And alpha is given, you can substitute directly. L by K, L is 8000, effective length is 8000, and we got the radius of gyration as 15. Substituting that, you will get Rankine's crippling load. It may be the column may be failing due to buckling or crushing. So Rankine's failure load as 6642.44 Newton or 6.642 kilonewton. So this is the Rankine's buckling load or crushing load. It may be buckling or crushing. So Rankine's failure load is given by 6.642 kilonewton. Now safe load is PR by 3, 6.642 divided by 3 or 2.214 kilonewton. So this is a safe load you can apply on the column. So safe load that can be applied on the column is 2.214 kilonewton. That's all for today. Thank you for watching.